The invisible engine of motion. How theoretical proof bridges the gap between seeing and understanding symmetry. The journey from observing a simple 3D arrow to witnessing a complex spinning vortex is mapped out by two critical guides. The state diagram, which charts our conceptual growth, and the sequence diagram, which details the software's technical heartbeat. However, the true significance of the entire project lies in the derivation sheet, which acts as the invisible anchor for both. In the context of the state diagram, the narrative begins with basic geometry, watching a position vector move while a gradient vector identifies the path of steepest increase. This is a world of static arrows. The derivation sheet is what allows this journey to progress by introducing a theoretical bridge. It transforms our perspective by shifting us from observing simple pointers to understanding physical operators. It provides the rigorous logic needed to move from a linear push, translation, to an orbital turn, rotation. Within the sequence diagram, the derivation sheet serves as the essential mathematical validation step within the software's internal engine. When a user interacts with the system to trigger a rotation, the software does not simply guess what a vortex should look like. Instead, it executes the logic proven in the derivation, specifically the fact that the order of operations in these calculations is critical. In standard algebra, certain products might result in zero, but the derivation sheet proves that for these specific operators, the result is a non-zero value that represents the rate of change of the rotation itself. Ultimately, the derivation sheet is what gives the visual animation its physical meaning. It explains the why behind the swirling vortex seen in the final simulation. While the state diagram shows us the path of learning and the sequence diagram shows the steps of execution, the derivation sheet provides the visual proof of symmetry. It demonstrates that these rotations are not just random movements, but are the fundamental generators that describe how a field behaves when it is turned in three-dimensional space.